So this is lecture 13, part 3, and I'm going to talk about the 3 types of dissolving reactions, dissolution reactions. And then any other related topics. At this point, it all kind of starts to blend. So primarily this is about ionic dissociation, molecular dissolution, and molecular ionization, and just a review slightly about the aqueous chemistry in general, because it's hard to separate them out completely. So we'll go to the slides. This set of slides is in module 8, is called acid-base theory. That's actually the second half of this slide set. So we talk about dissolution. What does dissolve mean? Dissolve actually comes from, find my notes. I'm gonna go to the whiteboard a minute, because sometimes I think having the origin of words helps remember or understand what it means. So we're talking about dissolve, and we're talking about substrates that dissolve in water, because this is aqueous chemistry. So dissolve comes from the Latin. Dis means apart, and solvere means loosen. So when you dissolve, dissolvere, you are loosening it apart. You are loosening your solute to where it falls apart. So it breaks down into its component parts, and that's where the word dissolve comes from, and it's also where the word solvent comes from. That's what's doing the dissolving, because the dissolving is a fact of intermolecular forces, and I'll go into that. But I showed the video earlier, 2 lectures ago, I think. So solvent also comes from solvere, to loosen. So this is the base of the word we use, and it also describes what's actually happening. Okay, so back to the slides. And we have 3 different reaction types, reaction equations for dissolving, for dissolution. The last lecture I talked about a precipitation reaction. That's when you already have dissolved solutions and you mix them together. So that's kind of the next step. So when you do an experiment, we talked before about how can you tell an experiment happens, a reaction happens, excuse me, a chemical reaction. You see a flame, you see smoke or vapor, you see color change, you might see a phase change. You see a solid appear in when you mix liquids together. Your solution starts to conduct electricity because of the new presence of electrolytes. Your solution acidity changes. It becomes more acidic or more basic. So even though we can't see what's going on at a micro view, we can tell something is going on from measuring the properties. And we can also learn about the extent of the change that occurs. That is going to come into play more when we talk about the acid base. So here are the 3 types of dissolution reactions. Now, there's a 4th category, and that is insoluble. All right. So we sometimes have a like magnesium hydroxide. If you say, what happens when you add that to water? The answer is nothing. If you get a question like that and you look it up on the table, nothing. It's insoluble. So that's the 4th option. But when you have substrates that dissolve, it's going to be one of these 3 reaction types. And the name of the reaction type tells you what's going on. And I'm going to go into each one. We have ionic dissociation, which I went into the first video. You have an ionic compound, and when it dissolves, it dissociates into its constituent ions. every ion is individually surrounded by water molecules separately. Those ions are called electrolytes, and they are what's responsible for, like salt water, conducting electricity. The presence of the ions. The more ions you have, the more electricity it will pass through, the greater current it'll carry. Molecular dissolution, and this really should be in the middle, is it's still dissolving. Okay, that's what dissolution means, but it's a molecule. It's a covalent molecule. So when this happens, this is not going to break up into its constituent carbons and hydrogens and oxygens. It will stay as a single molecule. Because if you remember that one of the differences between a molecule, a covalent molecule, and an ionic formula unit is a formula unit does not exist by itself. It's in a crystal. But you can have a single molecule, and that's what happens in dissolution, is the water surrounds that molecule and carries it off, but it's still one molecule and is completely surrounded by water molecules. Whereas the ions, its individual ions are surrounded. The third is molecular ionization. And it is again a molecule. This is an acid base. You start with the molecule on the reactant side of your equation, and your products are ions. So it creates ions. So this also creates electrolytes. So this does not. This is a non-electrolyte. There are no charged particles in a molecular dissolution. This is sugar dissolving in water. This is ethanol dissolving in water. That's our primary examples that we use for molecular dissolution. It is dissolving, but it's still a single sugar molecule. And you can taste the sugar, right? It's still sugar. It still has the properties. It can react with the receptors in your tongue that says sugar. So this video is just another picture of the different processes. Here's an ionic crystal, and the individual ions are being surrounded by water molecules according to the charge of the ion and the polarity of the water. Remember, water has a positive dipole moment, or two of them, and negative dipole moment. It has a more of a negative concentration, right? The polarity is up through the oxygen. So that more negative is going to be attracted to your cations. And see, there it is. There's the oxygen ends are butted up against the potassium, and your hydrogen ends are around the anion here. So in an ionic dissociation, your ionic compound dissociates. It breaks up into its constituent pieces, and each ion is surrounded by water molecules. Now, if you have a polyatomic ion, sulfate, nitrate, phosphate, the unit is surrounded by water molecules. It's still the polyatomic ion surrounded by water molecules. So if you had sodium phosphate, the sodium would come over here, and this would be the phosphate over here, surrounded by water molecules. This is a molecular dissolution. You have, like, this is a sugar molecule, a sugar crystal. The individual molecules are surrounded by water, but they are still sugar molecules. They do not break up any further. And this is how we write that equation. You're starting out with the solid sugar, and then you're saying, oh, I dissolved this in water, and this is what you get. You have a new phase. It's called aqueous, and that's what it means. It means dissolved in water. And that's all you have to write for molecular dissolution. It's the simplest one. Phases are very important at this point. So to remind you, the ionic dissociation, you start out with your ionic compound. It's a solid, because ionic compounds are, I can't think of a time when they're not solid. And then you have an arrow. You do not put water in the equation, okay? You do not put H2O on the reactant side of the equation for ionic dissociation or molecular dissolution. The water is shown with the AQ here. That is how we say dissolved in water. So this says, I took some sodium chloride salt, and I dissolved it in water, and it dissociated totally into sodium ions and chloride ions. And this is going to be a great electrolyte. It's going to carry a current really well. Sodium hydroxide, did the same thing. I took some sodium hydroxide pellets, which I can tell you, if you ever have to make hydroxide, add these slowly. It's a very exothermic reaction. It generates a lot of heat, and if you add them quickly, it'll boil over. So take your time. But anyways, the individual, this isn't really a very good picture, but I showed that video before. Individual ions are surrounded by water molecules. So that's ionic dissociation. And again, it has to do with the electrostatic potential. The ions are not sharing electrons. They're simply next to each other and all around there with that electrostatic attraction. So the poles on the water, the positive end and the negative end, are attracted to the opposite charges, and when you surround them, it's sufficiently strong enough to actually pull the ion out of the crystal and surround it completely. And every one that's pulled out, it creates more space for more to come in. More of the ions are revealed. Eventually, they're all removed. So it's intermolecular forces that cause this. Even with the sugar, it's intermolecular forces. From the regions of the sugar, there will be certain regions that are polar. And therefore, the water is attracted to those regions. And there's also something called hydrogen bonding, which you'll learn in Chem 1. If you have a substance that's completely nonpolar, go back to what we just learned about polarity in your structures, and you have one like CH4 that's completely nonpolar, it will not dissolve. Water cannot find a polar area to react with. So oil does not dissolve in water because oil is completely nonpolar and water is polar. So it's all intermolecular forces. When we have what's called an electrolyte dissolve, so that means it creates ions. And that means that it conducts electricity. So if you put a charged wand in there, and turn on a current, don't put your finger in, it's going to conduct electricity. Because of the ions, it's traveling across through an ion exchange. So it has got to have ions to be an electrolyte. Molecular dissolution, which is simply the molecule dissolves, but no ions are created, that is called a non-electrolyte. It will not conduct electricity. So we have strong electrolytes, weak electrolytes, and non-electrolytes. Non are the ones that do not create any ions. Weak, you're going to be introduced when we get to acid base. So right now we'll just say that's something that dissolves a little bit. It puts a little bit of ions in there, but not much. Your strong electrolyte is your ionic dissociation. You have an ionic compound that completely dissolves, so sodium chloride or potassium chloride, potassium anything, sodium anything. Now, one of the things with electrolytic properties, and you will learn this also in Chem 1, when you dissolve something in water, it actually changes the properties, the melting point and the boiling point. And that's why we add antifreeze to our radiators, because the process of doing that raises the boiling point and lowers the freezing point. That mixture, just a little side thing. Okay, so let's go back and look at those three the three reactions again. So yes, you will need to know how to recognize these, how to write these. But again, the name tells you what's going on here. So ionic dissociation, molecular dissolution, and molecular ionization. We're going to do that one last because that's acid base. So how do you write these? First of all, the ionic dissociation and the molecular dissolution, you do not put H2O in the reactant side, ever. We show it with this aqueous. But if you can write the products and balance this reaction without an H2O, you don't put it in there. So this is an ionic dissociation. I have an ionic compound. I'll go back and look, magnesium chlorate. Here's my rules. Right there, chlorates are soluble. We don't have any exceptions there. So therefore, if you put this in water, it will dissociate completely. So it dissociates into its magnesium ions. And here, remember what I said about polyatomics? This is the chlorate polyatomic. It just into the chlorate ion. It does not further dissociate into chlorine and oxygens. Okay, keep your polyatomic ions together as a unit. So keep it simple, really. Make sure you keep your stoichiometry. There's one magnesium, remember the little subscript? And there are two chlorate ion units. So I'm going to show one magnesium with a charge, and I'm going to show two chlorate ions. Your sides have to be balanced. This has a 2+. 2 times the -1 is -2, so this equals 0, and this, of course, is 0. One thing to watch for is as you start splitting these up, be careful when you write them as compounds again, you don't put charges in the compounds. Sometimes I see that. An ionic compound does not have a charge in it. It's only when you separate them. And then you have this phases. Solid, you dissolve it. Aqueous means dissolved in water. So this is ionic dissociation, as is this. You see it, you say, what kind of molecule is this? This is an ionic compound. Anything with potassium is automatically soluble. So you know, when I put this in water, it's going to split up. It's going to dissociate. Keep your stoichiometry. I have 3 moles of potassium ion here with my aqueous, and I have 1 mole of phosphate ion, aqueous. I have a 3- and I have 3 times the plus, so that's a 3+ and a 3-. My net is 0 over here, and that's what I'm looking for. So that's all there is to it, really, ionic dissociation. So if you're given this question, write the dissociation equation for ammonium sulfate. It can't be B because ammonium is always soluble. Any ionic compound with ammonium, potassium, or sodium is always soluble. That makes it really simple because those are used a lot. So anytime you see that, it's soluble. You don't even have to look it up. So my ammonium sulfate, first of all, you do need to know how to write. Your nomenclature is very important now. So practice that. Make sure because if your formulas aren't right, your equation won't be right. But it's going to go, oh, I tell you, I would have put one over here with the water in it. If you put water in an ionic dissociation on the left side, on the reactant side, it's wrong, just so you know. So it's going to dissociate into its constituent ions, right? Ammonium ion and sulfate. First of all, the charge is wrong on that, and these are written as solid. It's aqueous. You've put it in water, so you have to have the aqueous. So number 1, A is not right, B is not right. This has the aqueous, and it has the charges correct, but this formula is wrong. This says you have 2 sulfates. No, this gives you a 2 times the -2. This gives you a -4 and a +1. This is a -3 charge over here and a nothing over here. So there's your hint that it's not balanced. Here, your charges are balanced, except that sulfate doesn't have a -1 charge. Sulfate has a -2. So the answer is this one. You're keeping your stoichiometry correct. 2 ammonium ions, 1 sulfate, right? Here's 2 ammoniums, here's 1 sulfate. I have 2 times a positive 1 charge, so that's positive 2. I have a minus 2, so this is a net 0. And they have the aqueous phase here, which means dissolved in water. So this is why, and there's a lot of information packed into this one simple little reaction equation. So these are ionic dissociation that I've been going through. Those are just the, so let's go to molecular dissolution. This is the simplest one of them all. It's so simple that often when you work through the other two and you get one of these, you're like, wait, this is too simple. I'm doing something wrong. Because it's sugars and alcohols, which I'll go into the next slide to show you. This particular one is a peroxide. That's also a molecule that dissolves but does not dissociate. So peroxide, and it's a liquid form. Molecular dissolution, you can have a solid, a liquid, or a gas as your starting phase. Remember, molecules can exist as any of those. But your product is going to be aqueous. The molecule is dissolved in water. It's individual molecules are surrounded by water molecules here. So your most common examples that you're going to get, and so if you see either one of these in a question, you know the answer is molecular dissolution. Sugars, and sugars end in OSE. All sugars, glucose, sucrose, fructose, galactose, they all end in OSE. That's our naming for sugars. So if you see something that ends in OSE, you know it's a sugar. You know that sugar dissolves in water, but it does not dissociate. It's a non-electrolyte. It makes no ions, but it does dissolve. So you write it with the aqueous as the product. Alcohol is the other one you're likely to get. Any name that ends in OL, and the molecule will end in an OH. That's our writing system, formula system for alcohols. Alcohols, we write them, we end with an OH. And the name, stop that, ends in OL. So alcohol, ethanol, methanol, propanol, isopropanol, even glycerol. And these are all can dissolve in water, not methanol necessarily, right? Because it's nonpolar, but the rest of these are polar. Methanol, that has to do with its size. It's so small. You'll learn that next semester. So no ions are formed, very important. So it's a non-electrolyte. And the only thing you do is you write the original phase, and then you write the phase with aqueous, and that's it. Again, there is no H2O over here. If you put an H2O, it's wrong. So here we have a question. You have ethanol, but you know it's an alcohol because when you look at the structure, you see that. But you're going to be told, generally, the names. So you watch for that OL in the name. Stop. So what happens when we put ethanol in water? Okay, it's a molecular dissolution. So you have your starting phase. It can't be this one because it's not going to go to gas, it's going to go to aqueous, right? Like this one and this one. It is not going to break up into its constituent parts. That's not going to happen. It's going to do this. And this one is wrong because they've included H2O in it. That is not correct. The only thing you do is change the phases. And that says, I have just dissolved this ethanol in water. Okay. The third type is molecular ionization, and we're actually going to go in depth with this at the acid-base portion. And this is what happens when you have an acid mixed with water. Something very important to notice, this is HCl. When it's got a non-aqueous in front of it, we call this hydrochloric acid when it's dissolved in water, when it's aqueous. But this is not aqueous, this is a gas. This is hydrogen chloride. It's only when it gets dissolved in water that its acid properties come into play. So if you see this with a G or an L or an S, which HCl you won't, you give it the normal naming. Molecular ionization is called this because you start on the left side with molecules. These are both covalent molecules. Here you have to have water in the equation because it's the actual part of the reaction. A chemical reaction occurs between the water molecule and your other molecule. So in this case, it's an acid. What happens is the acid will donate its proton, in this case, to the water. You are creating ions as a result. Notice you have the aqueous dissolved in water. And so that's where your actual water is. You cannot write these products without H2O in the equation. You cannot say HCl yields H3O plus aqueous and Cl minus aqueous. So this is molecular ionization, and I'm just going to go to the board to show a little visual I do for acids. And again, we're going to go into this in much greater detail. When you have, so this is gas. So they actually bubble, they put the gas through a glass pipette and they bubble it in a beaker of water. The other thing to notice is H2O is liquid. H2O, you do not give it the aqueous. It's not dissolved in water. It is water. It's water in the liquid form, okay? So what happens, this is acting as a base. When we get into acid-base chemistry, you are going to learn that you have an acid and a base in every acid-base reaction. The base steals the proton, takes it. It does not steal a hydrogen. That is a proton. It leaves the electron behind. Now, a hydrogen does not have a neutron. So it's a proton and an electron. When you leave the electron behind, a bare proton is actually going over and joining in the form of hydrogen. Water. So water's stealing that because this is an acid. And so therefore water's acting like a base. Water can actually act as both, which you will learn. So when hydrogen chloride is dissolved in water, a chemical reaction takes place. And your products are ions. And now we say aqueous because now we are saying dissolved in water. Okay? When this proton joins here, I now have an extra hydrogen and a plus charge. And what's left, the chlorine, kept the electron. So it's an ion. So we had, you know, HCl. Remember that the Cl is very electronegative, so the electron cloud is going to be more like this. And then we have water with its unshared pairs. So it's going to come over and it's going to snatch the proton, and you are going to end up with H3O plus. So this is the chemical reaction that occurs. It's very specific with water. When you have an acid, something that has acid properties, this behaves as an acid with water. The H is in front of it. It's a way of writing it. So one of the keys when you're looking for molecular ionization is there an H in front of the molecule? So molecular ionization, molecules that make ions. These are electrolytes. So this will carry a charge. It'll carry current through it. You are going to learn a double arrow. This has a single arrow. This is called a strong acid, a strong electrolyte. That means 100% of it becomes dissociated, or not dissociated, this is the chemical reaction, but consumed. There is no more of this left. So when you see HCl aqueous, which is how we write hydrochloric acid, what's actually in that beaker is hydronium ions and chloride ions. That's what's actually in there, but this is how we designate it. So molecular ionization has to have the water because you cannot write those products without that. Do not do this. If you give me this, it's wrong. You do not have a bare proton as a product. That does not exist, and that is wrong. You must give me water and H3O+. This is hydronium ion. You need to know that, and also hydroxide ion, which is our base, and we're going to learn that in acid and base chemistry. So do not give me a bare proton. I don't care what you see in other videos online. This was, when I took Chem 1 at UF, my professor was adamant about this, and he was absolutely correct. And if you really wanted to get him upset, you gave him that, and he would get very upset because that's incorrect. This is what you write. There are no bare protons floating around. It's hydronium ion. So make sure when you're writing these, even if you see this somewhere else, do not give me a bare proton. Give me the proper equation. Physical states, balanced, right? We have a -1 and a +1, so this is a net zero. That's a net zero. This is a molecular ionization. So in this example, what would be the equation here for perchloric acid, except when this is dissolved in water? Well, our starting is gas, so that's fine. All of our starting units are correct. There is a reaction, it's very strong. It's not a molecular dissolution. It's chemical reaction with water. No, don't ever give me that. You are going to give me hydronium ion and perchlorate ion. However, the problem with this reaction, you cannot balance this. There's no way you could ever balance this because there's something missing from the reactant side. So D is the answer because you have your two reactants. This is a chemical reaction. You need two reactants, perchloric acid and water, to give you the perchlorate ion and hydronium ion, okay? So this is a summary again of the three equations. Ionic dissociation, watch the names. It's an ionic compound that dissociates. So you're going to start out with a single solid ionic compound, and then you're saying your product is aqueous, it's dissolved in water, and it's the two separate ions. Molecular dissolution, you have a molecule that dissolves, but it does not make ions. The starting molecule can be solid, liquid, or gas, and the ending is aqueous, dissolved in water. That's all you put. The molecular ionization, you have a chemical reaction, so you have to have two reactants. In this case, it's the acid and water. Again, this is an aqueous reaction, but water is reacting with this acid to give you hydronium ions and the anion. Now, you can also, these are examples where water is acting as an acid. You can also have water act like a base. There are times when water is going to give up its proton. So it acts as the acid. When you have a strong base, the strong base is going to actually swipe the proton from hydrogen, from water here, and you end up with an OH minus, a hydroxy ion, and whatever your base was that, swiped the proton. And again, you'll see that. I just want to point out that molecular ionization is not just, it doesn't just produce hydronium ions, it also produces hydroxide. Okay, so I'm going to go over to the board and we're going to work through these. Now, ionic dissolution, you're not going to get. from me. We don't bother with that here. So ignore it, but A, B, C, and E are all very good candidates. And I actually really like the structure of this question. So expect something like this on the exam 4, where you get a compound or a molecule and you have to pull down menu where you have to tell me what kind of reaction it has in water. So I'm gonna go over to the whiteboard. And the choices are, just don't have room. So we have ionic dissociation, molecular is dissolving, so it's dissolution. Molecular ionization, molecules that form ions as products, and insoluble does not dissolve in water, right? Because that's an option. That's part of your solubility. So the first one was zinc chloride. I'm actually going to go back to the slide for a minute because we're going to work through the solubilities of each of these. So first, let's just look at the solubilities of these, where is appropriate. Is zinc chloride soluble? Most chlorides are soluble. So if we go back to the rules, which I wish I had right next to the slide, right here. Most chlorides are generally soluble. Zinc is not an exception, but let's double check the table. And here's zinc, and chloride's the second one, so that says soluble. So zinc chloride is soluble, so that's good to know. The next one on here is HNO3. That's going to make, that's nitric acid, or it's hydrogen nitrate, but it's going to make nitric acid. It's got an H in front, and you will learn these when we go to the acid-base chemistry. So that is soluble. Magnesium carbonate. Well, if we go back to the rules, we'll see that most carbonates are not soluble. See, they're down here at insoluble. And let's double check the table. Here's magnesium. And we go down to carbonate right here, and there's the red, insoluble. So that one is insoluble. And then potassium nitrate, I don't even have to look that up because everything with potassium is soluble. Now, let's remind you, this is an ionic compound, right? Zinc is a metal, chloride is a nonmetal. Magnesium is a metal ion, carbonate is a polyatomic ion, so that's an ion with an ion. Potassium with nitrate is a polyatomic ion, so potassium, sodium, and ammonium are always soluble. And this is ethanol. It's not on our solubility table. Now I'll go to the whiteboard. We'll work through these now that we've looked up solubility. So zinc chloride, we looked that up when we said, yes, it's soluble. So here are my choices. You know, you have your pull down menu. I'm just taking it from that. Ionic dissociation, molecular dissolution, molecular ionization, insoluble. The first question you ask once you check solubility is this an ionic compound or a molecular compound, a covalent molecule. This is ionic. So we can immediately get rid of the molecular choices. So the next question that's left to us is it soluble? Yes. Therefore, it is an ionic dissociation reaction. And what's going to happen is your zinc now we can see up here. Your zinc chloride solid will dissociate into zinc ion, aqueous. Okay, that's how we know we've got it in water. We just told you with the aqueous. And there are 2 moles of chloride ion here, because chloride ion has a -1 charge. And again, that is aqueous. Double check your stoichiometry. I have 2 plus, I have a 2 times a -1, so I have a -2 and a +2, that's a net 0, that's a 0. That is the ionic dissociation reaction for zinc chloride. Ionic compound dissociates into its constituent ions in water, which we're telling you with the aqueous. Okay, what's the next one? HNO3, liquid. Okay. Is this a molecule or an ion? That's the first thing you ask. And actually, you can ask that before you look at solubility, because that only matters with ionic compounds. This is a molecule. This is a covalent molecule. Hydrogen acts as a nonmetal, remember. So it's not going to be either of the ionic choices. So it's molecular dissolution or molecular ionization. This tells you it's going to have an acid-base reaction with water. Therefore, it's molecular ionization. It's a molecule that is going to form ions. So when we put HNO3 with water, and remember water is L for liquid, we have a chemical reaction. Water is going to steal that proton. When this happens, you only get 1 proton at a time is removed. Yes, you can have more than 1 proton removed if there's more than 1 here, but it's 1 step at a time. So every reaction, you only show 1 proton being removed. So that kept, the nitrate kept the proton, the hydrogen's negative charge. It is now aqueous because it's in water. This ion is, and then we have hydronium ion. You're always going to get either hydronium or hydroxide ion in a molecular ionization reaction. Do my stoichiometry balances, do my charges balance? I have a -1, a +1, which is 0, that's 0. So that is my molecular ionization reaction for the HNO3, which is nitric, and we call that nitric acid. When you see it written as this, aqueous, sorry, my writing's not great. That's an aqueous. That is why we write nitric acid, and what it really means is it's nitrate ions and hydronium ions. But we write it like that. Okay, what's the next one? I'm going to change colors. I don't like all using just black. The next one is magnesium carbonate. Molecular dissolution, molecular ionization, insoluble. Okay, the first question you ask is this ionic or molecular? That's obviously an ionic compound. Magnesium is a metal. That's a polyatomic ion. So get rid of the molecular choices. Narrows it down right off the bat. The next question you ask is this soluble? Well, we looked this one up on the table and in the rules, and it said carbonates are generally not soluble. And we double checked it on the table and it said nope. So therefore, it's going to be insoluble. And if you would put that in water, You have no reaction, or you say insoluble. Preferably you say insoluble, but really either one. It's just going to float there, this white powder floating on top of the water, just looking at you like, yeah, and. Okay, so that is insoluble. That's your choice. Because you looked up the rules and you saw that carbonates are insoluble. And then if I gave you the table, you can double check the table. I happen to like using tables, but you do need to know the common rules. Okay, the next one, I'm going to write my choices first. So the next one is potassium nitrate, solid. Okay, so we have some solid potassium nitrate we're going to put in water. What will happen? Is it ionic or molecular? That is obviously an ionic compound. You have potassium, which is a metal, and the nitrate, which is a polyatomic ion. So it's ionic, so we get rid of the molecular choices. Now you have two left. Is it soluble? Anything with potassium is always soluble, always. Therefore, it's an ionic dissociation. And what's our reaction? You're going to say this, and it dissociates into its ionics. And you tell me that it's in water with the aqueous. So you're saying, I took some solid potassium nitrate and I dumped it in a beaker of water, and I now have potassium ions and nitrate ions surrounded by water molecules. And we would call this potassium nitrate solution. If I take this and I dump it in, or we make sodium chloride solutions all the time in the lab. We call it a sodium chloride solution, and we give a concentration to it. Remember that molarity? We will give it a concentration. We'll say you have 5 molar, potassium nitrate, aqueous. That's how you would label it. So anytime you hear solution, you know it's dissolved. And if it's an aqueous solution, it's dissolved in water. Okay, so the last one is ethanol. So we have some liquid ethanol, and you're going to add that to water. Now, if you remember the rules about sugars and alcohols, you won't even have to ask the question, but it doesn't hurt to go through it. Is this an ionic compound or a molecule? It's clearly a molecule. Those are all nonmetals. It's covalently bound. So we're going to get rid of the ionic forms. OH means alcohol, and the name is ethanol. And when you see that OH on the end, that's alcohol. So that is going to be, it's going to dissolve in water. It is not going to make ions. When it dissolves, it's going to be single ethanol molecules surrounded by water molecules. And that's it. That's all you write. So that's molecular dissolution. So those are the reactions. And then the previous recorded lecture was about aqueous reactions, which is you have two solutions. So we've already done all this. And you have two solutions that you made through ionic dissociation. So they're full of ions. And now you've mixed them together, and now you're asking the question, do you get a precipitation out of this? Do you get a product? So that was the previous lecture, specifically talking about aqueous reactions. And for that, you have two reactants, both aqueous, both in solution. And then you're looking to see, when you rearrange those ions, do you get something that is insoluble, like that magnesium carbonate was insoluble? But the initial step is dissolving it, right? Before you can do solution chemistry, you have to make a solution. So this is about making a solution. What's the process? What do you have in your solution? Do you have a bunch of ions? Do you have a bunch of molecules? Or do you have a a pH, high or low pH? You have an acid or a base? Or do you have white stuff or floating around in there or blue stuff because it's not soluble? So that is the end of this part. Practice it. Go through a series of steps where you always approach it the same way. Don't put water where it doesn't belong. And don't give me any bare protons on the product side, because those are wrong. Remember your phases. Remember to keep your charges balanced. And really think about the names of these dissolution types, these reactions, because that tells you what's going on. And save the memorization for things that you have to memorize. And you just use this more as understanding, because the more you understand in chemistry, the more you get it, and it builds on it, and it becomes more part of you, and you get to where you get so used to doing it, you don't have to think about it. Or you can recall, because you understand. You can go, oh, well, this is this. Oh, right, that's that. Okay. You can get from here to there. All right. And so this is the end of lecture 13, part 3. So this is the end of lecture 13. And then the next one will be acid-base reactions, lecture 14, which will be probably 2 videos.